have a reaction here. I have a nickel here and I have a silver here. For this, reaction is nickel solid becomes nickel 2 plus aqueous, and then I have Ag plus aqueous gives Ag. Right? I have to find the Nernst equation for this, assuming they are not 1 molar. First, write the balanced equation of the cell. The balanced equation is nickel solid reacts with, or if you want to find the first half, the electrode reaction reward at cathode, nickel becomes nickel 2 plus, it gets 2 electrons, and here Ag plus will take 2 electrons to becomes 2 Ag. Correct? 2 reaction. This is at anode oxidation, this is at cathode reduction. Let's sum up this reaction. You get nickel plus 2 Ag plus will give you nickel 2 plus plus 2 Ag. That is my reaction, right? Cell reaction. That is my cell reaction. And 2 electrons are used. I can just use my Nernst law formula. E cell is nothing but E naught cell minus RT by NF, N is 2, F ln of concentration of Na2 plus, concentration of Ag is 1 because it is solid, divided by concentration of Na is solid 1 and concentration of Ag plus, they are 2 Ag plus, so it will be square because there is nothing but ln of K. So that is the Nernst equation for this reaction. Correct? Let's see some application of Nernst equation. It is used to find EMF of the cell at any given concentration. That is, we have seen the most important role of Nernst equation. It is also used to find equilibrium constant. You see the Nernst equation has a equilibrium constant E is equal to E naught minus RT by NF ln K, right? So this equilibrium constant we can find. You can also use to find the Gibbs energy of the reaction, right? Because you have the K, you can find the Gibbs energy of the reaction minus NFE, right? Gibbs energy, and you can find the E, you can find the Gibbs energy of the reaction. We'll see some numericals on this aspect. So let's take one example here. First, we will represent the cell in which the following reaction take place. Mg is getting oxidized to Mg2 plus, and Ag is getting reduced from Ag plus to Ag. This is oxidation, and the other is reduction. First, to represent the cell, so we can represent in this fashion. Mg is becoming Mg2 plus, oxidation. The concentration of Mg2 plus is 0.13 m, and then Ag plus concentration is 0.0001 m is becoming Ag. That is my cell representation. Now you have to find the E cell if standard E naught is 3.17 B, right? So we know that E cell is nothing but E naught cell minus RT by NF ln K. So let's put the value. What is E cell? E naught cell 3.17 volt minus RT by NF. Or we can just, since these are happening at 298 Kelvin, assuming at standard room temperature, this becomes 0.059 by NF, sorry, by N. And N is what? 2 electrons, because 2 electrons are getting transferred here, right? Mg becomes Mg2 plus 2 electrons, 2 Ag becomes Ag, 2 electrons by 2 into, this becomes log, and K is what? Concentration of Mg2 plus by concentration of Ag plus whole square, right? I write here. K is concentration of this by concentration of Ag plus whole square, because there are 2 here. So let's put the value here. So Mg2 plus is 0.13 by, this is 0.0001, and this is square. Correct? This becomes log, because we have seen the formula E is E naught 0.059 by n log k. That is also there, right? So we have used that formula here. So this becomes, you solve this, this is 3.17V. You solve this is 0.21V. And the answer is 2.96. So if you see, there is a drop in voltage. The standard voltage is 3.17, but the actual voltage is 2.96 because the concentration is not 1 molar. See, as I told that Nernst equation can be used to find equilibrium constant. Right? So the equation we have, E cell is nothing but E naught cell minus 2.303 RT by NF log of Q. So there is a mistake here, this is Q here. Correct. Now this at equilibrium, what will happen? Q will become K, and at equilibrium the cell will become dead, so E cell becomes 0. Please note, E naught cell will not become 0, this will become 0 because the cell will become dead, right? So at equilibrium this will become 0. E naught cell is a standard value, we know we can't change this, minus 2.303 RT by NF, Q becomes K. So with this, log K is nothing but E naught cell into NF by 2.303 RT. That is the formula. With this you can easily find the K equilibrium for a cell. Correct? See, for Daniell cell, let's find this. For Daniell cell, let's find this. For Daniell cell. For Daniell cell, log K is equal to E naught cell, we know is 1.1 volt for Daniell cell. N 2 electrons. F we know is 96487 coulomb by 2.303. R we know 8.314 and T is 298 Kelvin. Let's assume the normal temperature. We solve this, you get 2 into 10 to the power, sorry, you'll get the value of K, 10 to the power 37. Because it's log K, you solve this, you get some value. This actually you get, this is 37.288. Yes. So log K is 37.288, so K becomes 2 into 10 to the power 37 at 298 Kelvin. So we have to find the equilibrium constant for this reaction. So we know that E cell is nothing but E naught cell. Let's assume that this is having a 298 Kelvin. Use the shortcut formula, minus 0.059 by N log of Q. Right? So at equilibrium this is 0 and Q is K. I can say this is 0 equal to E naught cell minus, and this for this equation N is 2, right? Copper becomes Cu2 plus, so there is 2 electron, 0.059 by 2 log of K. And E cell value is given, that is 0.46 volt, right? This is also in volt, volt cancel. So if you solve, log of K is nothing but 0.46 into 2 by 0.059, that is nothing but 15.6. That means K equilibrium is nothing but 3.92 into 10 to the power 15, and that is my answer. Correct. Thank you.